Welcome to Ingenium On Demand.
Hello, Ingenium attendees. My name is Shawn Ramos, and I am a recent graduate from the University of Manitoba. I'll be discussing my thesis project on hemodynamic effects in foreshortened endovascular aneurysm repair limbs. I have been advised by Dr. April Boyd and Dr. David Kuhn, and without their expertise and advice, would not have been able to complete this thesis project. A brief agenda for today's presentation can be seen on the slide. The presentation will start with background information, as well as objectives and rationale for the project. Next, the methods performed to complete the study are discussed. The results are then presented for the steady state flow cases, and then the results for a specific endograft limb investigated with pulsatile flow are presented and discussed. Next, the wider relevance and importance of the study are discussed, followed by conclusions. Abdominal aortic aneurysms, or AAA, is a condition where the aorta becomes enlarged due to risk factors such as smoking and genetics. Endovascular repair, also known as EVAR, is the current preferred method to repair AAAs as it is less invasive than open surgery. Endografts are devices used for EVAR and are typically stent graft systems. The figure on the right shows an enlarged aorta, also known as a AAA, as well as other arteries which endovascular repair devices attach to. The main body of the endograft attaches below the renal arteries of the aorta, while the endograft limbs attaches above the internal-external artery bifurcation. To study the hemodynamics within endografts, computational fluid dynamics, or CFD, can be used as a non-invasive tool to observe how blood flows in the vessels. CFD is based on mathematical models to describe the fluid flow. Important formulas and theories which CFD is based on include the conservation of mass and Navier-Stokes equations. For turbulent flows, there are numerous models available, with the K-epsilon model being a common one. From the literature review, while CFD to evaluate hemodynamics in AAA is a generally accepted practice to predict locations of rupture, CFD to evaluate hemodynamics in endografts and endograft limbs is a generally new practice. The main objective of this thesis was to determine if foreshortening specific endograft limbs leads to significant changes in hemodynamic conditions that predispose to limb occlusion. The rationale behind conducting this thesis was that intraluminal thrombus has been identified as a major cause of all graft occlusion, including within endografts. Hemodynamic factors such as low velocity and areas of recirculating flow have shown a correlation to the formation of intraluminal thrombus, which may lead to limb occlusion. It was hypothesized within this thesis that endograft limbs which experience a significant diametral change from foreshortening may negatively affect hemodynamics, leading to flow recirculation and intraluminal deposition, which may ultimately lead to limb occlusion. A summary of the methods followed within the thesis are shown on the slide. 3 endograft limbs were investigated in the study, and they were a 16mm diameter case made by manufacturer A 16mm diameter endograft made by manufacturer B, and then a 10mm diameter endograft made also by manufacturer B. The study began by getting physical measurements, followed by generating CAD models, and then generating a mesh for the 3 cases. And then a steady state simulation was performed for each of those 3 cases. Following that, a grid independent study was performed. Then I moved forward with the 10mm manufacturer B case for pulsatile analysis based on Dr. Boyd's observation and recommendation that these limbs have a high frequency of occluding. Independent studies such as cycle independence, grid independence, and time step independence were all performed for the pulsatile simulation. For the physical measurements, Silicone putty molds were created for each of the 3 endograft limbs by placing silicone putty within the endograft. The molds were then measured with a compass and a ruler to obtain the dimensions. CAD models were then generated based on the physical models, and an example of the 10mm manufacturer B geometry is shown on the slide. Note that when foreshortened, a pentagonal internal geometry was observed along 2 locations. A similar geometry was observed in the 16mm manufacturer B case. From the CAD models, mesh was generated using the automatic meshing function in ANSYS CFX. A tetrahedral mesh was used for each of the 3 cases so that a finer mesh could be applied around complicated geometries. For the simulation parameters, blood flow parameters were based off of Lazawi's study on the relationship between pulsatile flow impingement and intraluminal thrombus deposition in abdominal aortic aneurysms, specifically taking the values for blood density and dynamic viscosity. For the boundary conditions, no slip walls and 0 gradient pressure at the outlets were applied based off of methods outlined by Lazawi as well. For the inlet condition, a constant radial flow was deemed acceptable for both the steady state and pulsatile flows, as the length from the inlet and geometry disruptions allow the flow to become fully developed. The flow rate for the steady state case was assumed to be 2.5 liters per minute based off of an average iliac flow rate, which was based on a normal cardiac output of 5 liters per minute. The flow rate for the pulsatile case varied as shown on the figure on the right, which was based on experimentally obtained results for an infrarenal flow rate divided by 2 because of the bifurcation from the aorta. A turbulence model was applied as diseased arteries have been observed to cause turbulent flows. As the endograft limb geometries more closely depict diseased arteries, a turbulent flow was assumed in this study. A K-epsilon model was used for the rate at which convergence can be achieved and relatively low computational requirements required relative to other models. For the manufacturer A case, the flow is quite uniform. The effect of foreshortening on this limb only reduced the diameter by 0.2 millimeters. Since there are no significant geometry disruptions, we see that the flow is uniform at the diameter reduction, where there is a slight increase in velocity, and the velocity further increases once the limb bifurcates. As reattachment points are defined where there is a sign change in wall shear stress, also denoted as WSS, there are no recirculation zones observed in the 16mm manufacturer A case. This meets expectations as there are no significant geometry disruptions with this endograft limb when it is foreshortened. At the bifurcation, a slight change in the wall shear stress is observed and plateaus off. The shear stress increases at the bifurcation as the fluid flows through a smaller diameter where the fluid accelerates. Since an increase in the near wall velocity is related through a logarithmic relation to the shear stress, the increase in shear stress is expected. For the 16mm manufacturer B case, qualitatively on the figure on the left, recirculating zones can be observed directly following both pentagonal geometry disruptions. Since the wall shear stress was observed to change signs 4 times throughout the length of the endograft limb in the longitudinal direction, recirculation zones for the 16mm manufacturer B endograft limb have been confirmed for the steady state case simulation. Similarly, for the 10mm manufacturer B case, recirculating zones can be observed directly following both pentagonal geometry disruptions as shown again on the figure on the left. Of the 3 cases, the 10mm manufacturer B case was observed to have the greatest velocity along the center axis of the geometry disruption, which is expected due to continuity. Again, the wall shear stress changed signs 4 times, resulting in 2 recirculation zones for the steady state case. The main takeaways from the steady state results are that the geometry of foreshortened manufacturer B limbs created recirculation zones following the pentagonal diametral reductions. The greatest reattachment length was observed in the 16mm manufacturer B case, with reattachment lengths of 2.8mm and 15.6mm respectively. A grid-independent study was conducted, and further refinement is necessary in the manufacturer B cases following the second pentagonal diametral reduction, as the size of recirculation zones are highly sensitive to the grid. Moving into the pulsatile results for the 10mm manufacturer B case, as the inlet velocity approaches peak magnitude of the pulse, areas of recirculation are observed as shown in the figure on the slide. Recirculation zones are identified by negative velocities where flow is moving in the opposite direction of the inlet, shown in the darker blue color. These areas are located within the foreshortened section along the edges, as well as immediately following the foreshortened section along the edges of the endograft. At the bifurcation, a faster velocity is observed on the inner portions, which may be explained by jet structures created by the foreshortened section, which concentrates the flow directly to the bifurcation. At the peak inlet velocity of the pulse, a recirculation zone along the edges of the foreshortened section are observed as shown on the figure on the slide. Immediately following the foreshortened section, along the edges is an area with a recirculation zone and/or stagnation zone. These two contour plots were shown as even in systole, or where the inlet flow is accelerating. Recirculation flow is still observed in the endograft limb and is magnified relative to what we would expect during diastole. The key takeaways from the pulsatile results is that the maximum velocity observed within the 10mm manufacturer B endograft limb was observed at the peak inlet velocity, which was expected due to continuity. Based on the figure on the right, there appears there may be a correlation between Reynolds number and reattachment lengths, where negative velocities are observed. An experimental study on a closed forward-facing step performed by Essel et al. Was shown to have such a correlation and may explain why the minimum velocity was of greatest magnitude at the greatest inlet velocity within the endograft. Similarly, for the steady-state case, further refinement is required for the grid following the foreshortened section, as currently the recirculation zones may be exaggerated due to the sensitivity of the results from the grid. Additionally, a smaller time step should be utilized in a future study to represent the transient flow more accurately instead of representing a series of pseudo-steady-state cases. However, a coarse time step was selected due to computational limitations due to performing most of the study remotely due to the COVID-19 pandemic. Although not a recommended practice, vascular surgeons foreshorten long endograft limbs to ensure there is a good seal between the connection to the main body of the endograft as well as to the common iliac artery. Furthermore, foreshortening is done to allow flow to the internal iliac artery and external iliac artery. Blocking the internal and external iliac arteries may cause colon death, loss of the ability to walk, and the loss of the ability to have erections. Therefore, the thesis has a wider relevance, showing that there are significant flow differences between foreshortened endograft limbs made by different manufacturers, which may lead to thrombus formation and limb occlusion. With further investigation, this may lead to the practice of foreshortening specific devices being completely avoided by surgeons, or may lead to a redesign by engineers of the devices to limit the geometry changes when foreshortened. In conclusion, the initial scope was inclusive of steady state and pulsatile flow conditions for each of the 3 endograft cases. However, due to delays obtaining representative endograft geometries, and again, the time computational heavy resource requirements for CFD simulations, the scope was reduced to steady state flow conditions for each of the 3 cases, and then 1 pulsatile flow condition being investigated. Future work is required to strengthen the findings of the thesis. In this study, an idealized endograft limb geometry or geometries were utilized in this thesis. In the future, patient-specific geometries should be investigated, which would also factor in angulation and tortuosity. Additionally, physical experimentation could further strengthen the findings to compare to the CFD simulations to observe how well the CFD simulations represent the physical system. Nevertheless, the key takeaways were that recirculation zones were observed in the steady-state manufacturer B cases and not in the manufacturer A case. A potential correlation between Reynolds number and reattachment length may exist within the foreshortened manufacturer B endograph foreshortened geometries. With a foreshortened manufacturer B geometries disrupting flow, specifically creating areas of low velocity and areas of recirculating flow, these factors have been observed to be areas where thrombus formation is likely to form and may ultimately lead to limb occlusion, resulting in negative patient outcomes. That brings me to the end of the presentation, and I would like to thank Ingenium and the association for providing a platform to share my thesis. Thanks, and bye.
Thank you for watching. Visit the Ingenium On Demand library for more exclusive content.